Okay, so I'll continue then with the alternative solution. There is an alternative. There's another way to solve the same problem. And how do I solve the same problem? Okay. The way to do that, to solve the curved beam problem, is to start with the equilibrium equations. You can then use the compatibility equations. And you can see here, I have two equations, and you can use these two equations to manipulate them and to solve for this radial stress and tangential stress. You can see I have two equations and two unknowns, sigma r and sigma theta theta. So that's an alternate way of going about this. And when I actually do that work, I'm not going to do it here, but Mathematica or MATLAB can actually do this. You can then get the expression for radial stress and hoop stress by solving the equilibrium equations and then solving for the compatibility equations. You're able to find this. The good news is when you impose the boundary conditions, by using these equations, you get the same answer as I got just a second ago, which is this one here. You get this here using the boundary conditions for the curved beam. What about the problem of a shear load? I have a shear load applied here. In the earlier problem, what I had was a bending moment applied. But in this problem, I have a shear load applied. And the question becomes, what is the stresses in this beam due to applying a shear load here? Again, the benefit of the area stress function, what is the benefit? The benefit of the area stress function is that it allows you to solve problems in an easier way. The boundary conditions look a lot more complicated, but I'll step you through each of them and ensure that you understand what we're talking about. So why don't we start understanding what this is? So this is a curved beam with a shear load applied here in the top surface and is clamped here on the left side. The inner radius is A, the outer radius is B, and theta starts here at the top. It's important to understand where theta starts is in the figure. Theta starts at theta equals 0, and it goes all around to theta equals pi a half. Hopefully everybody knows that's pi a half. And so what I'll do now is step through each of the boundary conditions and make sure you understand them. So sigma r is the radial stress, and I'm looking at A comma theta, and sigma r B comma theta is 0. Why is that 0? So let's think about what this is saying. What this is saying, and you should come up with the boundary conditions. You should understand how to come up with the boundary conditions. Looking at r equals A, which is this surface right here, that surface right there, and r equals B is this surface out here, the outside surface, while r equals BA is the inner surface. For any value of theta, obviously, because theta is kept as a variable, that means I'm looking at any value of theta. So anything along these two surfaces that enclose a body of material. That radial stress has to be 0 because I'm not applying any radial stress here. You can see here, there's no radial stress being applied. So that makes total sense. No radial tractions are applied. I'm not applying any internal pressure or external pressure. We also see that the tangential stresses at those two surfaces here and here are 0. We understand that too, because there's no traction loads applied on the outside surface or the inner surface. Any questions about those two boundary conditions before I move to the next boundary condition? It's very similar to what we did before. Now let's examine together what's going on at this surface right there. That surface right there has a load applied this way, the shear force. And for that nature, looking at this, using Cauchy's relationship, if I were to draw a square here, and I were to write a square there, you can see here that's the r direction, that's the theta direction for that square. And you can see here that there's a load applied that way. And that load is sigma r theta equals that load P. But that sigma r theta is getting integrated with dr, and it assumes that there's a thickness T, but I didn't put the T there, which is fine. It's unit per unit length. It's load per unit length. That's another way of doing it. So you can see here that P is the resultant force, shear force in that direction, and And you can see there that we accounted for that in that formula. Now, looking at the next one, let's look at the next one. The next one is this 2 here. And what you see here is that at R, so at this surface right here, sigma theta is pointed perpendicular to this surface. Sigma theta is pointed perpendicular to that surface. You can see there's no resultant force. I'm not applying an axial force. I'm not applying an axial force. There's no axial force. Q is 0. And I'm not applying any moment. So moment is 0. So therefore, this right here should be 0 as well, because there's no sigma theta being applied, and there's no moment being applied. The other thing to note here is, by equilibrium, it should make sense to you that I apply a load P here. Sorry about that. I apply a load P here, but that load P is reacted this way as well, right? So therefore, there is a sigma theta in this surface. That sigma theta is evaluated at theta equals pi half. Obviously, I'm looking at this surface where theta is pi half. And if I took a square here and I drew it, that's going to be your theta direction. That's your radial direction. And you can see that I have a load applied this direction, P, right? So therefore, the integral between this point and this point, the resultant force has to be minus P. And it's minus P because it's pointed against the surface. Okay. Then I have this next one here, sigma r theta over here. There's no shear forces being applied on that surface, so that's 0. Okay, so there's no shear forces being applied on that surface. And then I left this to the end for a reason, because that one took some thought. But let's look at the moment now. Okay, so there's a moment acting on that surface, and let's understand how that moment is taken care of. So you can see this shear force is going to cause a moment. It's going to cause a moment here. And that moment should act in this direction to counteract this force P applied. That's a reaction force there. And that moment is going to have to be that force P times the distance. The distance is between this and this, correct? So what is that distance? The distance is A. So A plus this distance here, which is B minus A divided by 2. And when you do that, you get P A plus B divided by 2. So you have a moment resultant on that particular surface. There is a question, let's take that. When I look at the solution for this problem, the solution is actually very complicated, and somebody worked it out to be this particular area stress function. And that area stress function can then be used to calculate, you can actually show that that satisfies the biharmonic equation, exactly gives it equal to 0. And you can also show that by using phi, this phi, particular phi, that when you plug it into the stress formulas that are in terms of area stress functions, you get that these are the stress functions for that. Please. Let's cover that maybe in a discussion session, because that will be a mathematical thing to do. Is that fine? Or what if I give you 40 points extra credit, because this is a purely mathematical thing, right? So what if you guys tried it by next week and you learn how to do it? Maybe watching YouTube or something like that. Is that fair? 50 points to try it? You should get this to 0. So if you plug this in here, you should get 0. Let's YouTube it. Let's look. 50 points for you. And talk to my TA for discussion session as well. Okay, so when I do that, I get the stress components to be this. And how many unknown coefficients I have? A, B, and D. How do I calculate those A, B, and D? Boundary conditions. I also have C, but C does not show up. It turns out that when you actually solve it and you apply all these boundary conditions, there's many of them. Remember, 1, 2, 3, 4, 5, 6, 7, 8. There's like 10. But some of them become redundant, it turns out. And when you apply the boundary conditions, you can solve for A, B, and D, and the stresses become this formula that you see here. And notice how theta shows up now and how the radius shows up. So now when you plot stresses here, they become a function of theta and r. So this varies. The stress, the radial stress varies, but now shear stress also showed up. That showed up. So in the final exam, I could ask you, hey, do this problem, but tell me how to use Mohr circle for this. You should be able to do it because you can draw a square. And if you draw a square, you should be able to draw a square, get what the value is at that point. So that point, say, has coordinates of, say, 5, 90 degrees. You should be able to plug that in into this formula and get sigma RR, which goes this way. Sigma theta theta goes that way. And the shear goes that way, sigma r theta. If I know the stress state for in a square that I can draw, I should be able to use Mohr circle very straightforwardly. So that is going to come up potentially in the exam for you to practice at. Okay. So that's a formula for curve being under shear load.